Hi, my name is Yuxi.
Hi, my name is Julia Saucedo.
Hi, my name is Nikita Patel.
Hi, my name is Sanjana Bandlamudi.
Today, we will discuss the topic of flows in prose media and some real-world applications. I'll introduce what flows in prose media is, explain the two mathematical models, which is Darcy's law and the Brickman equation. And my teammates will discuss three applications that directly relates to Darcy's law and the Brickman equation. So first, what is prose media? Prose media are solid materials with internal pore structures, which allows fluid to flow through. The pores can be either empty or filled with fluids. These diagrams labeled A, B, C, and D shows different types of pore structures that are important for diverse real-world applications. Picture A on top left is an example of regular array cylindrical pore structure. This uniform circular pore structure are commonly used in water filtration system to remove contaminations from drinking water. The form structure on top right is typical of natural porous rocks such as sandstone. Picture C on lower left is an example of granular structure. This structure can be used as reactor column catalyst. The fiber matrix example at lower right is usually used in drug delivery. The mathematical tools we use to model this system are Darcy's law, which applies to laminar flow, and the Brickman equation, which accounts for more complex flow conditions. And I'll introduce Darcy's law first. The interaction between solid and liquid phases in porous media was first quantified by Henry Darcy in 1856. In a study of water percolating through sand, Darcy discovered that the flow rate was proportional to the pressure gradient. The relation is called Darcy's law. The equation shown here expresses the relationship for a homogeneous and isotropic medium, where V is the fluid velocity averaged in the ReV. ReV is the representative elementary volume. Delta P is the gradient of the hydrostatic pressure. H is the hydraulic conductivity. H can be written as K divided by mu, while K is the hydraulic permeability of the medium, and the mu is the dynamic viscosity of the fluid. While Darcy's law has broad applicability, it also has some limitations. It cannot be applied to non-Newtonian fluids, Newtonian fluids at very high velocities, such as blood, and gases at very low and very high velocities. From the physical point of view, Darcy's law assumes that the viscous resistance at the fluid-solid interface is much larger than that within the fluid. This assumption is valid only when the specific permeability K of porous media is low. However, when K is large, the viscous stress within the fluid cannot be ignored, and the momentum equation is derived using Stokes' equation for low Reynolds number flow, which is called Brickman equation. As shown here, Darcy's law can be considered as a specific case, as case one when the permeability is very small, the viscous resistance at fluid-solid interface, which is the first term in the equation, is much greater than the viscous dissipation within the fluid, which is the second term in the equation. In case two, when the permeability is very large, the viscous resistance at fluid-solid interface is much smaller than the viscous dissipation within the fluid, which recovers the Navier-Stokes equation. This picture shows some common applications of fluids in porous media. The picture on the top left is an example of gas-capped oil reservoir. The picture on top right is a tissue scaffold. The picture on lower left is a carbonate acidification, and the picture on lower right is an example of water filter. Sanjana will introduce case study one.
Hello everyone. Today I will discuss how the concepts we've studied, such as Darcy's law and the Brickman equation, are applied in a study on oil well productivity. The study integrates multiple flow regimes to model fluid behavior across different regions of a perforated well, demonstrating the direct use of these theories in engineering challenges. A major challenge in this field is accurately predicting well productivity. Productivity depends on two main properties: porosity, which determines storage capacity, and permeability, which governs fluid flow. To extract hydrocarbons, perforations are created in the well casing and cement sheet to connect the reservoir to the well bore. This is complex because fluid flow from the reservoir through the perforations and into the well bore involves different scales and flow regimes. The paper seeks to address the challenges of modeling flow in perforated wells where fluid moves through distinct regions with varying physical properties. To capture this multi-scale flow behavior, the researchers developed a sophisticated model that integrates Darcy, Brinkman, and Navier-Stokes equations, known as the Debian model. This model assigns the appropriate equations to each flow region, ensuring a comprehensive representation of the fluid dynamics within the well. They also analyzed how parameters like perforation size and permeability affect well productivity. In the undisturbed reservoir, the flow can be modeled with Darcy's law. However, as the fluid converges into the perforations, the flow velocity increases and Brinkman's equation becomes more appropriate. Finally, inside the wellbore itself, we have a relatively open space, and Navier-Stokes equations govern the flow. To understand the flow behavior within a perforated well, we need to revisit the fundamentals of flow in porous media. The study relies on three governing equations. Darcy's law describes fluid seepage in porous regions like the reservoir and damaged zones. It assumes low speed flow and negligible inertia. In the perforation tunnels, the Brinkman equation extends Darcy's law by including viscous shear stresses. This transition is critical as flow accelerates. Finally, the Navier-Stokes equation models fluid flow in the wellbore, where both inertial and viscous forces dominate. Together, these equations enable us to capture the multi-scale nature of fluid flow in oil wells. The authors divided the well into 5 zones, each governed by different flow equations. The 5 regions are the reservoir, damaged and crushed zones near the wellbore, perforation tunnels, and the wellbore itself. In the reservoir and damaged zones, Darcy flow dominates as the fluid moves slowly through a porous structure under a pressure gradient. Here, inertia is negligible and resistance to flow is proportional to permeability. As the fluid enters the perforations, flow accelerates and viscous shear becomes significant. The Brinkman equation models this intermediate regime, balancing Darcy-like resistance with additional viscous stresses. Finally, in the wellbore, the Navier-Stokes equation applies, accounting for both inertia and viscous forces. The coupling of these equations across boundaries ensures a smooth transition in flow properties, which is key to accurate modeling. Boundary conditions play a critical role in linking these regions, ensuring pressure continuity and mass conservation. The simulations were performed in COMSOL with fine meshing in areas like the perforations and crushed zones to improve numerical accuracy. Assumptions such as steady state flow and uniform permeability simplified the complex physical system for computational feasibility. Using the Debian model, the researchers performed a series of simulations to investigate the impact of various parameters on perforation completion productivity. Their findings reveal that the permeability of the perforation tunnel itself is the most critical factor. Blockage in the perforation significantly reduces productivity. The productivity ratio index derived from Darcy's equation quantifies these effects. The results reveal that perforation parameters such as permeability, diameter, and density are key to optimizing productivity. The study also highlights how damaged and crushed zones reduce permeability, creating bottlenecks in flow. Pressure drops deeply in the perforations and wellbore, aligning with the Brinkman and Navier-Stokes regimes. Velocity peaked at perforations, demonstrating the importance of transition modeling. Validation against experimental data confirmed the reliability of the numerical model with an R-square value of 0.979, ensuring high confidence in the results. This model has practical implications for the oil and gas industry. They highlight the need to prevent perforation blockage during production and to carefully optimize perforation parameters during the well completion phase to achieve maximum productivity. Now, Julia will take over to discuss the second case study.
Hello. Case study 3. So in case study 3, the paper explores the contributions of the Brinkman equation in modeling reactive flow during carbonate acidification. And it's focusing on its performance compared to the Darcy equation. It does this using a 2-scale continuum model that studies and analyzes how different terms in the Brinkman equation affects fluid momentum balance during varying flow conditions, porosity, and permeability. So some of the results shown in the study is that the Brinkman equation provides more accurate predictions in scenarios involving high injection velocities or free flow regions, such as fractures or wormholes, where the Darcy equation underestimates critical dynamics. This has significant implications for applications in enhanced oil recovery and CO2 reinjection strategies. So going into the case overview, the study, as I mentioned, examines reactive flow during carbonate acidification, a process critical for CO2 sequestration and enhanced oil recovery. So acid dissolves carbonate rock and increases porosity and permeability, and it's forming new pathways like wormholes in the process. So excuse me. The focus is on accurately modeling flow in vuggy carbonate rocks, which is the figure demonstrated in this slide. Which have large cavities and fractures. So these highly heterogeneous structures make modeling challenging, as Darcy's law assumes uniform flow and neglects viscous stresses and accelerations, factors critical in high velocity or high permeability systems. The researchers compared Darcy's law with the Brinkman equation, and they wanted to see which one was better able to capture fluid dynamics in complex porous media. So they did this using micro-CT imaging. They modeled porosity and permeability fields with high accuracy. And so this study directly connects to class concepts like porosity, permeability, and the transition from Darcy to Brinkman flow. So, and it's able to demonstrate real world applications for improving predictions in complex systems. So a better approach. So Darcy's law as we all know, assumes uniform flow and neglects viscous forces, which work for low permeability systems, but fails in vuggy rocks with fractures or voids. So these conditions create significant viscous interactions and accelerations that Darcy's law doesn't account for. So the Brinkman equation bridges that gap by combining Darcy's law with Navier-Stokes elements. And so it adds viscous stress within the fluid for high permeability regions and acceleration terms for fast moving fluids to capture momentum effects. So this makes the Brinkman better suited for modeling flows in heterogeneous porous medium. So this slide is just to demonstrate the methods used. The researchers used 2 main steps to compare the equations. They used micro-CT imaging and simulations in open foam. So they simulated acid injections under varying conditions to track changes in porosity, permeability, and dissolution patterns. What we got from this slide was that they were able to better identify where Darcy's law failed and where the Brinkman equation was able to excel. So in conclusion, the studies clearly demonstrates that the Brinkman equation's advantages over Darcy's law for modeling reactive flow in complex medias by accounting for that viscous stress and acceleration effects. Brinkman provides more accurate predictions in higher permeability systems with voids, and it better models flow pathways, wormhole formation, and permeability changes during acid dissolution, which is very important. So these findings have significant applications in industries like CO2 sequestration and enhanced oil recovery, where accurate flow modeling reduces risks and optimizes processes. The use of the micro-CT imaging, as we mentioned, further highlights the values of the advanced tools for reliable simulations. Now, Nikita will go over case study 3.
Hello, this is case study 3, linear stability of a filtration flow with gas-oil interface within the Brickman approach. This problem models the vertical flow stability in an oil reservoir with a gas cap. The objective of the authors of the paper, they want to model the fluid flow through porous media under varying conditions while considering both low velocity flows governed by Darcy's law and higher velocity flows near boundaries, where the Brinkman equation is used to account for shear stress and viscosity effects. The key challenges of gas-capped oil reservoirs are: 1, pressure drop causes the oil-gas interface to shift. As seen on the picture on the right, the gas covers the oil. So when the area is drilled to remove the oil, this interface causes the gas to leach into the production wells and residual immobile oil formation. Additionally, the interface instability fragments the flow of oil. To rectify this problem, the authors are modeling the movement of oil in porous media, and they're making the following assumptions. 1, a horizontal reservoir, as seen in the picture in the previous slide. 2, a gas cap above the oil, and a high permeability interlayer or fracture below the oil. And 3, oil flow is incompressible. Using these assumptions, they use the generalized Brinkman filtration equation to describe oil movements, where μe is the effective dynamic viscosity. This is the basic equation they use throughout their research to model the flows across the reservoir while accounting for pressure changes and viscous effects. Using that Brinkman equation, they derive the gas-oil interface movement, or H of T. From here, they derive the dispersion equation to examine flow stability using both Darcy and Brinkman approximations. The diagram on the right shows the result of graphing these equations. Line 1 shows Darcy's law, and line 2 shows Brinkman's law. This is the result of modeling the dimensionless growth rate versus the wave number. As you can see from the diagram, Darcy's law is an infinite growth rate, while Brinkman's is more of a bounded, finite growth rate. When we can compare Darcy and Brinkman approaches, we examine where they come from. Darcy assumes μe is equal to 0, which means it's good for large-scale flow with an infinite wave number growth. It's assuming laminar flow, which means it's insufficient for smaller instabilities and is unable to capture the flow for an unstable system. Brinkman's does not assume μe is equal to 0, which means it incorporates viscous shear effects, making it ideal for small-scale phenomena and making it effective for modeling interface dynamics and instability transition. As a result, we see that Darcy predicts infinite instability flow because it cannot handle the short wavelength perturbations. Meanwhile, Brinkman predicts dampening or neutral flow for very high wave numbers, which gives us a bounded growth rate for perturbations. In conclusion, Brinkman's approach is more suitable for modeling complex flows and instability in porous media. The key findings of this study was that both Brinkman and Darcy can be used to approach flow models across diverse regions of porous media, accounting for pressure-driven flows in regions with viscous effects. While Darcy's law captures the permeability of media for large-scale flow, Brinkman's shows the viscous effects at boundaries or regions of lower permeability. This helps us predict how fluids behave within gas-oil reservoirs, which are naturally occurring porous structures. In return, this research can be used to aid in oil recovery, hydraulic fracturing, and drilling and welling stimulations. The study of flows in porous media has widespread applications for modeling flow in oil reservoirs, as we saw throughout this presentation, or to designing filtration systems for biomedical and environmental applications. By understanding the mathematical basis of Darcy's law and its underlying physics, we can develop models and predict flow behavior. As we move forward, we will continue to utilize this fundamental basis for advanced computation techniques and to address complex global challenges. Thank you.